I'm Zhiqiang Shen from Shanghai Astronomical Observatory. So the time here is late evening. So I would like to say good evening or good morning or good afternoon, depending on where you are. Anyway, I'd like to welcome everybody to the second day of Event Horizon Telescope, next NG Event Horizon Telescope Science Workshop. So this is the first session for the second day. We will have two invited talks. The first one is given by Maria Rioja. And I think Maria is well known by VLBI people. She has been working on the VLBI astrometry for about 20 years. And in particular, she's an expert for the phase referencing technique, which I'm sure will be very, very helpful for the ngEHT project. So I think the presentation is pre-recorded, right? So please play.
Hello, my name is Maria Rioja. My background is on VLBA and astrometry. First of all, I would like to thank the organizers for the invitation for this talk. The last decade, together with Richard Dodson, we have been focused on the development of phase calibration strategies, matching the capabilities of next-generation radio instruments. Below is the review paper that contains a comprehensive description of those. It is a pleasure to present our experience with multi-frequency calibration at millimeter VLBI and the applications to the sub-millimeter regime to this audience. This is the outline of my talk. I will start with a brief mention on some of the challenges at high frequencies related to fast tropospheric fluctuations that limit its sensitivity, astrometric measurements, and hence its applicability. Then I will argue that multi-frequency calibration can reverse those effects. I will give a presentation of the basic demonstrations and benefits of multi-frequency calibration strategies applied to millimeter VLBI, followed by the prospects for application in the sub-millimeter regime in the context of the increase in effective coherence time, reduction of clock noise, and enabling space VLBI observations. Finally, a summary and next steps in our investigations. The figure shows a variety in the nature and size of the elements in a VLBI array in the era of the next generation of instruments. Alongside the moderate-sized single-disk telescopes, there are the large collecting areas provided by a massive single-disk or a connected array phased up, and also the extremely long baselines provided by a radio telescope in space above the atmosphere. New technologies are fundamental. On one hand, multi-pixel capabilities for large single-disk arrays illustrated with narrow orange cones can provide matching fields of view, shown as light orange cones, from all of these elements for multi-view calibration strategies, particularly beneficial at the low frequencies. For observations at high frequencies, multi-frequency receivers, illustrated with the two-tone incoming waveform, are a powerful tool for millimeter VLBI, provide the capability for simultaneous multi-frequency observations for FPT and SFPR calibration strategies. These next-generation technologies, combined with the next-generation methods, will deliver a significant improvement in performance across the radio spectrum with the next-generation instruments. Phase referencing techniques carry a relevant role in VLBI, enable the imaging of weak sources by extending the coherence time and precise astrometry measurements. Here plotted with colors are empirical results from the literature, shown with symbols, and theoretical expectations with lines from applications of PR in black and related advanced tropospheric and ionospheric calibration techniques in green and blue respectively. These are traditionally used to reverse the contaminating contributions to the phase observable, for example arising from the non-dispersive tropospheric fluctuations. But this strategy breaks at about 43 GHz. Instead, multi-frequency strategies like SFPR and FPT continues to deliver these benefits beyond the thresholds or phase referencing-based methods. Demonstrations up to 130 GHz, which is the current highest frequency of the KVN, show extremely good performance, hence are relevant for ngVLA and ngEHT frequencies. Basically, phase referencing relies in interleaving observations of a nearby calibrator to eliminate the tropospheric fluctuation and extend the coherence time, with telescopes switching backwards and forwards with a duty cycle that matches the fluctuations. Higher frequencies require faster telescope switching. This strategy breaks because there is a limit to how fast a telescope can move and the availability of calibrators, which is, as mentioned, 43 GHz. An alternative strategy consists of using transfrequency calibration. Remember that the phase tropospheric errors are proportional to frequency. Color code throughout the presentation is red for low frequency and green for high. At heart is similar to phase referencing, with the roles of sources and frequencies interexchanged. Frequency switching can be easier operation than source switching, therefore faster duty cycles are okay. It was first tried with VLBA using fast frequency switching, and the upper frequency limit is 86 GHz, twice as for phase referencing. The multifrequency receiving system of the KVN is an engineering development to address this issue, using simultaneous multifrequency observations. It results in a superior calibration which is applicable up to much higher frequencies, demonstrated with KVN up to its highest frequency of 130 GHz, no known upper frequency limit. It truly opens up a path towards enhanced performance in the high frequencies regimes. Some of you may be familiar with a related method called band-to-band as used on ALMA long baseline observations. Here is a quick overview of the basic of the frequency phase transfer multifrequency strategy. Following the standard nomenclature for VLBI observations, these are the phase residuals at the two frequencies, with contributions from troposphere, ionosphere, instrumental, and from the source, buried under all of the rest. Some contributions change slow, some fast, as indicated with the labels. The frequency phase transfer calibration consists in using the analysis of the observations at the lower, easier frequency as reference to calibrate the higher frequency observations, after scaling by the frequency ratio. After FPT calibration, common contributions at both frequencies are eliminated, such as the tropospheric. The rest remains, such as the ionosphere, which propagates from the lower reference frequency, hence becomes larger and instrumental, and in general any dispersive error, and also any difference in source position at the two frequencies that carries the astrometry signature. But the important thing is that only slow changes remain. Therefore, the pre-calibration with the observations at the lower reference frequency significantly increases the coherence at the higher frequency compared to single frequency observations at the high frequency for follow-up self-calibration analysis. Effectively, the multi-frequency calibration is equivalent to a quality upgrade in the weather conditions and the telescope site. An alternative option to the self-calibration step is to include interleaving dual-frequency observations of a second source, which are used to eliminate the similar ionospheric residual error contributions. This is the basis of the so-called source frequency phase referencing analysis. Because the remaining FPT error terms are slowly varying, slow telescope switching is okay. Also, the source can be far away. This two-step calibration eliminates propagation medium and instrumental errors. It is equivalent to observations from an excellent site and with a perfect instrument. It boosts the sensitivity by reducing coherence losses. Also provides a precise astrometric registration of the images at the two frequencies. For example, to discuss course shifts without ensuring bona fide astrometric image registration is close to meaningless. A quick summary of the multi-frequency calibration presented. They offer a most effective way to compensate the fast phase changes due to water vapor in millimeter VLBI, the outcome being 2 orders of magnitude increase in coherence time compared to single frequency observations. Here shown an example of multi-frequency calibrated phases at 130 GHz for the 3 kVn baselines, and also enable bona fide astrometric registration between observed frequency bands, which we call chromatic astrometry. Shown a movie of astrometrically registered multi-transition water and SIO measures emitting at the 4 kVn bands, 22, 43, 86, and 129 GHz, located in a circumstellar envelope of an evolved star and spanning 2 years. The domain of application is the high-frequency regime. Note that also compensates for antenna coordinate errors, being non-dispersive. Hence, these techniques are relevant for space VLBI observations. Best performance is obtained from simultaneous multi-frequency observations. This is the compact triple-band receiver, which is being rolled out in multiple European stations developed by Dr. Han in the labs of CASI. It is a very active field of research applied to a large number of observations, mostly from KBN key science projects. I note a couple of multi-frequency contributions in this meeting. Here you can see multi-frequency calibration in action with real data from KBN observations of 5 quasars at the 4 frequency bands. Here shown are the raw residual phases at 22 and 44 GHz for the 3 kVn baselines versus time 9 hours for one of the sources. The residuals are dominated by tropospheric fluctuations, which impose faster phase changes at 44 GHz. This is the same dataset at 44 GHz after frequency phase transfer calibration using the scale solutions from 22 GHz, multiplied by a factor equal to 2. The results show that the phase residuals at 44 GHz change slowly and are similar for all sources, now being dominated by ionosphere and instrumental residuals. The superior atmospheric compensation effectively results in an upgrade of the site, stabilizing the atmospheric conditions. Same at 86 GHz, above the raw phase datasets, and below after using frequency phase transfer calibration using the scale solutions at 22 GHz. And again, 88 GHz, now using 44 GHz as the reference frequency. It delivers even higher phase stability. And here at the highest frequency, 132 GHz, after FPT calibration using the scale solutions at 44 GHz. The effective coherence time at 132 GHz after frequency phase transfer calibration is 20 minutes. That's a 100-fold increase. As all sources show similar dominant dispersive contribution, we use a differential analysis between pairs of sources. That is the basis of SFPR. Shown here is the worst, most extreme case in our sample. At 130 GHz, the target source did not have direct detections and the reference source is 11 degrees away. The source frequency phase reference calibrated phases are now quasi-free of propagation effect, with an effective coherence time of 8 hours at 130 GHz. Also shown in this high-quality source frequency phase reference map with 80% flux recovery, a proxy for the coherence loss. I note that a smaller source pair separation result in less than 1% flux losses. Next, I am moving to the applications of multi-frequency observations at ngEHT frequencies. In order to show the prospects of multi-frequency calibration to increase the coherence time in the sub-millimeter regime, I have rescued some simulation studies we did in 2012 with a range of frequency pairs, namely at 4386 GHz, shown in red with crosses, 87 and 175 GHz, green circles, and at 175 and 350 GHz with blue and plus symbols for under so-called very good weather condition, that is typical weather at ALMA site, shown on the left, and for good weather conditions, shown on the right. We generated synthetic simultaneous dual frequency datasets using the interferometry simulator ARIS for the three pairs of frequency, and carried out FPT analysis with a range of solution intervals at the low frequency. The frequency phase transfer datasets were Fourier transformed to generate images. Shown in the plots are the corresponding fractional flash recover versus the solution interval time. Note the counterintuitive behavior where the highest frequency pair have the best performance. This is due to reduced dispersive ionospheric residuals remaining. Also shown in the top right are the values obtained using frequency phase transfer plus a further self-calibration iteration, following the same color and symbol codes. Our simulations show that even at 350 GHz, very small coherence losses, about 5% under very good weather conditions, can be obtained with integration times of many minutes, if the data are pre-calibrated using observations at 175 GHz. An alternative option to the self-calibration step is to use source frequency phase referencing, that is, include interleaving dual frequency observations of a second source every few minutes. The choice of fast frequency switching or simultaneous observational capability is critical. For guidance, we turn to our ngVLA community study, using the coherence losses as a figure of merit. The plot shows the fractional flux loss in the SFPR images versus target frequency. Black hexagons are from actual SFPR experiments using KVN simultaneous observations, and cyan stars are from VLBA with 60-second switching. Green circles are from ngVLA simulations at 30 seconds. The lines show results from an approximately equal metric for various switching cycles, and the black line overplotted on the x-axis is for simultaneous. Performance deteriorates towards higher frequencies and longer switching cycles, but simultaneous show no deterioration. To extend this analysis to ngEHT regime, we have used the same data and extrapolated up to 900 GHz. The points are as before, and estimates from a 10-second cycle shown with the blue line are additionally plotted. The results show that simultaneous dual frequency observations are most desirable in the ngEHT regime. A 10-second cycle might be okay, but we would need to repeat these simulations to be reassured. Other than the tropospheric fluctuations, the noise from the hydrogen measure frequency standards can be a significant contribution at the ngEHT frequencies under the best so-called very good weather conditions. In 2012, we carried out simulation studies to assess the benefits of replacing the H-measure with the cryocool Sapphire Oscillator CSO, which was developed by the group led by John Hartner at UWA at the time, whose stability is more than one order of magnitude better. The graphic in the lower left corner shows the clock and atmospheric instabilities with Allen standard deviations coded in the ARIS simulator. We proceeded to generate a synthetic dataset for observations of a source with flux density 10 Jansky, and carried out self-calibration analysis and images using a range of solution intervals. The plot shows in red the peak fluxes and in the image using the hydrogen measure and the CSO for the multiple solution intervals, and in black the percentage change between both. We found that at this frequency, the advantages of using a CSO over the hydrogen measure are negligible. Nevertheless, at 350 GHz and under the best weather conditions, the hydrogen measure losses introduce significant error within the time scale equivalent to the same coherence loss. Using a CSO results in a 15% increased sensitivity compared to an H measure. The reason why this is relevant to the topic of multi-frequency calibration in this talk is because the clock noise from the hydrogen measure, being non-dispersive, would also be accounted for, that is, calibrated out in dual frequency observations calibration strategy, which save us having to implement much more expensive CSO clocks in the array. Last but not least, the application of multi-frequency calibration techniques for space VLBI. Space VLBI observations at high frequencies hold the prospect of achieving the highest precision measurements. Nevertheless, space-specific issues such as limited accuracy in the satellite orbit reconstruction limit the application. Instead, multi-frequency techniques naturally addresses those, and a satellite antenna orbit error is readily compensated, along with any other non-dispersive error, such as tropospheric fluctuations with observations at two frequencies. We investigated its feasibility in the context of VSOP2 at the highest frequencies, 22 and 43 GHz, using simulated datasets for space-ground VLBI observations under a range of weather, here shown as good, typical, and bad, and orbit errors, among other parameters. All details are in the publication. Here just show a couple of plots to highlight the results. So, simultaneous dual frequency calibration continues to be robust with the space VLBI observations against different weather conditions. That is, turn a bad day into a good day. That is, reverses the effect of bad weather, delivering a sustained coherence and astrometric accuracy of 1 microarc under different weather conditions at 43 GHz. And it is also robust against satellite orbit errors, that is, reverses the effect of telescope position errors and provides sustained performance under a range of simulated errors up to 130 centimeters. Now, of interest for the sub-millimeter regime, the specifications of the millimeter space mission equipped with a multi-frequency receiver, for example, the new 5 bands KVN multi-frequency up to 230 GHz, are compatible with requirements to carry out successful FPT and SFPR observations in order to increase coherence time and VLBI observations with the space mission, and also astrometric measurements. And this is my summary. Sub-millimeter VLBI observations are an exciting but hostile environment. It is worth throwing all tools available to overcome the limitation. Simultaneous multi-frequency receivers are a key engineering development to address the root issues. I have shown how a significant improvement in performance comes with FPT and SFPR calibration strategies up to the highest frequency available, 130 GHz. Prospects for sub-millimeter VLBI are very promising. FPT and SFPR provide robustness by effectively upgrading the telescope site, which will result in more telescopes being able to join the ngEHT array, and moreover facilitates sub-millimeter space VLBI. About our next steps, we continue the empirical explorations with the rapidly increasing network of telescopes equipped with multi-frequency technology.
Okay, thank you, Maria. So I think Maria is available, so we would like to invite some questions for Maria. You can raise a hand in Zoom. So Shen.
Yeah, so very nice, Maria. Wonderful presentation. I'm a little bit interested in the flux density limits. So what kind of faint sources do you think you can use for calibration in this method? And then related to that, for Sagittarius A star in particular, the lower frequencies can't always be used on the long baselines to use this technique. So is there something we could do for that source as well?
So the requirements for these multi-frequency techniques is that you need to have direct detections at the low frequencies. So it's a bit like phase referencing, that you need to have direct detection of the reference source. Here you need to have a direct detection at the reference frequency because this is your reference.
But I guess the point is for Sagittarius star. Sagittarius star is scattered. So for the lower frequencies, you may not be able to get a detection at the lower frequencies.
Yes, in these cases, this might not be the most appropriate, I guess.
But you could use a second source.
Yep.
A second source, like phase referencing.
Yes, so you make Sagittarius not return. It'd be a bit difficult.
I mean, yeah, of course, you could do inverse phase referencing, which is referencing with respect to a calibrator, basically.
Okay,
Yes.
Thank you.
But the requirement for these methods to work is you need to have detections at the low frequency. Okay, and then at the high frequency, you can integrate much longer, and then is where you build up the signal to noise ratio. But your solutions comes from the low frequency.
Okay, so Shrita line.
Okay, thank you. A very nice talk, Maria. I had one question. You know, your technique, of course, addresses a wide range of issues. You know, not just tropospheric. You know, clock errors. It addresses all sorts of things, which is wonderful. My question is about the use of water vapor radiometers, which can handle the tropospheric fluctuation part. You know, the water vapor part. So what is the relative comparison between the two? Do you have an idea? Are you able to comment on that?
So water vapor radiometers, certainly they've been around for a long time. I think the ones in ALMA, they were pretty well, but I don't know the performance of the water vapor radiometers in sites which are not of the excellence of ALMA.
Yes, so they, for example, Pletcher Debut, I believe, uses a 22 gigahertz water vapor radiometer. You know, 22 gigahertz line is more suited for sites which are not so great, so good as the ALMA site. I was just curious the relative merits of these techniques, because your technique, of course, is wonderful because it addresses so many different aspects.
Yes, so if you are calibrating along the same line of sight, yeah, I mean, it allows you also for astrometry. You also, I mean, collect data at the multiple frequencies. So it's also a very efficient use of the time, of the observing time.
Right. But in the context of the situation like what Shep brought up, where the lower frequency detections may not be possible, then you're left with something like the water vapor radiometer, right?
Yeah,
so that is the context of my question.
Then you would want another method, either water vapor radiometers or phase referencing with respect to another source. Yes, definitely, that would be a way very complementary of the two techniques.
Okay, thank you.
Masha. Masha.
Hi, yes, thank you. Very, very good talk. I very much enjoyed it. It wasn't clear to me on, I think it was your figure 8 on the clocks, on the use of the Sapphire CSO clock versus a hydrogen maser, why the dual frequency would remove errors, the clock errors for like multiple sources. If you were looking, say you're nodding between a source and a reference, it seems like the clock error is still there. You're just removing it in your dual frequency stuff, but not in that global sense, in that bigger sense.
The plots that I saw, they are analysis with self-calibration. So they suffer from the noise in the clocks. Okay, if you would have a dual calibration, is because the noise of the clocks would be in both being is also a non-dispersive contribution, is independent of a frequency, and then when you make your frequency phase transfer, that you use the residuals at the low frequency to calibrate the high frequency, you get rid of it. You eliminate it in the same way that you eliminate the tropospheric errors and the antenna positions for space VLBI, and the noise of the maser is exactly of the same nature. It's only that the noise of the maser, it's something that you only get to see when you have got rid of all the other effects. Let's see, it's like when you correct an effect, there is another one that becomes a dominant. So the noise of the maser will become visible if you have observations at very high frequencies and if your atmospheric errors are very small. Then it is I mean, they were simulation, of course, data sets.
Has anyone ever used a CSO for VLBI?
I don't think so. Not that I know of. But also going in VLBI to these high frequencies is only in the last years.
I mean, do you think that would be worth doing engineering tests with?
I would say yes, of course, but we also think that they might have a better performance in this niche of very high frequencies and absolute very small tropospheric errors. Then the next thing that will come will be the noise from the clocks. But we also believe that multi-calibration will calibrate it out. I mean, I think that the price is quite a consideration as well would be to equip the antennas with CSOs.
Well, there's also, I don't think we have any operational experience. I don't know if anybody really does.
Yes.
So that's an issue.
Yeah, it's true, but I mean, yes, I think heading to the high frequencies and trying to get higher and higher and higher precision, we always find a new source of error, no? So probably after when we have a perfect compensation of the tropospherics, it will be the noise of the masers.
Well, of course, and they're always more expensive to fix too.
Yes, yeah, yes.
Thank you very much. It's a good
Yes,
talk.
you're welcome. Thanks.
Shen.
Okay, why don't I reach to ask my question? Great talk, Marie, and it's wonderful to see you almost like in real life. And surprisingly, I have a question also regarding the clock. So we all know that if we self-calibrate with a short solution interval, there is a risk that we generate a signal from the noise, right? And when you take care on the clock, it is exactly what you do, right? You most probably have to work with short solution intervals. So how do you separate so solving your case and the correcting for the clock from generating a fake signal from the noise, or at least partly generating fake signal from the noise?
You don't separate, you just correct. It's a bulk correction, no? It's like in phase referencing. You don't separate what is troposphere and ionosphere. It's a bulk correction. You estimate you make standard self-calibration analysis. At the low frequency, the residuals there, they will be a combination of all of the errors in your a priori models: troposphere, ionosphere, instrumental, clocks, position errors of the telescopes, everything. So in this, because if they are non-dispersive nature, they are identical at the high frequency. Particularly, they are along the same line of sight and at the same time, as are the multi-frequency observations. So it's just like a bulk correction of the whole thing.
Your other effect could be multiple baselines. More antennas.
I couldn't hear that when we were speaking.
In the background, you mean? Richard,
Maria, we can hear you fine, Maria.
Fine.
Yes.
Yes, Judith, sorry. Have I explained myself, or
Yes,
you have something?
Yes, I apparently have some worries because we do have seen fake amplitude, right? So amplitude going up, which is not a result of astrophysical signal, but a result of short solution intervals, which you use in your self-calibration. And but I'm sort of repeating myself, so let's continue discussing it in Slack. Thank you.
Okay. Yeah. Great.
Yep.
More constraints is more antenna.
Wants to ask a question.
Yes. So we can't hear Shen, but I guess it makes sense for Gopal to continue, right?
Okay, I guess I'll ask my question. Maria, great talk and great results. I had a question. As you know, with the ngEHT, we are planning a dual frequency 230/345 gigahertz receiver.
Mm-hmm.
In your talk, you gave some wonderful results of extrapolating between, I guess it was simulations between 170 to 350 gigahertz. My question is, if you actually had a third band, say 86 gigahertz band, as is being debated within the ngEHT community now, if you had three frequencies, could you do a very good job extrapolating between 86 to 230 to then to 345? Is the bootstrap work as well, in the sense that if you don't detect, say, 86 gigahertz, as has been discussed, say, because of scattering on Sagittarius star, can you use the 230 detection to do a better job at 345? I'm guessing the answer is
yes, I think so. Yes, I mean, having the only thing is that if you might have noticed that I kept using integer ratios in our pairs of frequencies. This is our experience with the KVN observations is because when you multiply the phases at the low frequency and you have there a number of phase ambiguities that you of course don't know. If you use an integer number, you don't, let's say, disturb the number of ambiguities. They continue to be an integer number of ambiguities and that's it. If you go with a non-integer number, you unleash there in a way the number of ambiguities that you haven't taken care of, or that you don't know how many unknown number of ambiguities. So then it needs we also have done this type of observations with the KVN. For example, when you have frequencies that they have to be like maser emission, for example, from water to SIO, that they are not an integer ratio. And there's, you need to have better a priori, you need to have a more closer monitoring in time, because there is this additional issue that you have to deal with, that when you multiply your ambiguities by a non-integer number, this is going to turn into not a whole cycle, but you are adding there a fraction of an ambiguity to your phases. Okay. So, three frequencies would be, yes, when we heard yesterday about the option of the 86, yes, we think it's a very good idea to include 86. On the other hand, 86 also and 350, they are an integer ratio of 4.
Okay.
But yes, having multiple frequencies, it would help you probably to give it more flexibility to try, you know, maybe variations of the methods that I have talked about, which probably they are necessary to develop bespoke methods for the sub-millimeter regime and in other cases like scattering and sources. I'm sure there would be a way forward. Yes, they provide a lot of flexibility.
Thank you.
Maybe I impose myself on the last question, but so there's always a trade-off between the phase noise at the reference frequency and the ratio between the reference and target frequency. Yes. So what is the best combinations of the two? Because yes. If you start with 86,
yes. So the best thing is that you would have frequency ratios which are as small as possible. That is definitely the thing. Also because you are multiplying, you know, you're in particular, well, at these high frequencies, it might not be very relevant, but in the KVN, we could see if your reference frequency is 22 and you go, one of the plots I showed, it was referencing 88 gigahertz from 22. And it's okay, it stabilizes the phases, but if you use 44 as your reference frequency, is better, because at 44, the ionospheric is smaller than at 22. So you don't carry so much ionospheric errors to your high frequency. And also, as you say, you are multiplying your errors by, you are scaling. You scale your phases and you scale your errors as well. So yes, it's a budget of what is the signal to noise ratio and so.
So thank you, Maria. I think our chair has lost connectivity.
Has gone.
So I'm going to step in and
use that fact as much as we could. Yes, sorry.
Thank Maria again, but I do think
Yes.
we need to move on.
Yes. Thanks for your interesting questions and attention. Yeah.
Thank you. Okay, and next in the schedule we have Antonio Stamerra. Antonio, are you there?
Yes, I'm here. Good afternoon. Well, good afternoon for me. Good morning for you, or most of you, and good evening also to Maria, as far as I understood. Okay, my talk, I will go now directly, if I can start, and after thanking Avery, Michael, and the others for inviting me to this nice venue. And my talk will go directly on the other side of the electromagnetic spectrum, and we will now start to talk about gamma rays. Now, I try to share my presentation, which I do not see. Okay. Can you see it now? Maybe?
We see yours. Yeah, now we see.
Do you see? Oh, okay.
Yes.
Can you see switching? Okay. Fine. So I can move on. And then, as I said, my presentation is related to gamma ray observation, and specifically, I will describe you the Cherenkov telescope array, CTA. And I will try to demonstrate you, but you already know from your past experience with the ngEHT that multi-wavelength observations up to gamma rays are important. And this was already shown yesterday in the session, in the plenary session that you had yesterday. So first of all, just to trying to set the stage, I give here a set of questions, of open questions on AGN and gamma ray blazars, which are holes, let's say whole, not just for gamma ray observations, but in general. But of course, gamma rays are the one that most, as also radio actually do, but gamma rays are the one that trace the non-thermal emission from AGNs. As you can see in the sketch on the right, I mean, these are the main typical examples of emission processes, leptonic, so electrons or hadronic, that we think happen in a jet, I mean the relativistic jet. And the still open question is how this jet is formed. Which are the main features of the jet: magnetism, shock formation, and also the composition. If we have in the formation in the base of the jet, this is more magnetic and then more heavy. I see some noise. Can you hear me? Is it fine? Yeah. Okay, and also, from the point of view of gamma rays, we are interested in how gamma rays are produced, the one that we see, and all the physical environmental conditions there. Of course, all these main processes or main questions are related to very small scale regions. So, which goes from the really near the black hole, the supermassive black hole, up to the parsec region, for example, the borderline region of Taurus, so this kind of thing. And I think you are well aware of that, so I will not explain you how to go deep into the details of a black hole in the jet, and this is a figure that you know very well. But I would like to focus. I mean, it's clear that radio has as the lead in going deep into near the black hole. And instead, on the other side of the angular resolution, we have gamma ray observatories, which have resolution of the order of degrees, or let's say a few tens of degrees. And so my point now is the point I want to make is how from this observation we can also infer something in the near small scale near the black hole. And there are different way to do this. The first one is definitely variability. So the variability you see in gamma rays is very, very fast variability. It's very short. So we can see, and you see here some example of what I'm talking about. For example, the M87, you know very well, in the flare where it lasted just let's say less than 1 day. And if you compare this variability of less than 1 day with the typical light crossing time of a supermassive black hole typical of M87, and you compare them, you will see that the 2 times are very much similar. What does it mean? Well, it simply means that the emitting region is a small one. Now the next question is where this emitting region is if it is a single region or if it is a sort of accumulation of many emitting regions with substructures. For example, what you see here also from the light curve that you see here in the bottom, as a function of time, you have the flux at energies higher than 200 GeV. You see that very high emission, and on top of that, very small peaks of a minute scale. And also historically speaking, on the right, bottom right, you see what maybe one of the first evidence of minute scale variability in AGN, or in this case, blazars that you know. And so the question is really, is this small region nearby the black hole at the base of the jet, or is somewhere else? Now, trying to understand to this question, there were also other observations in the past years. One of them is on IC310. This is a radio galaxy in the Perseus cluster. Maybe you recognize here the optical figure, historical figure, together with some radio contours. Here the Perseus cluster, and here IC310. And actually, this is a nearby radio galaxy, and from VLBI, where you can see images from VLBA jet, VLBI jet, and VLBA here on the right, and where you can clearly see the one-sided jet, meaning that the angle is a small one, so you can infer the Doppler factor around 6 here. And here in this other figure, you see the discovery map, sky map, where we detected the IC310 almost by chance, or well, not really, but serendipitously, we can say, because we were observing in reality NGC 12 or 3C84, as you like to call it. So, and from this source, the interesting thing that we found was the very rapid variability. As you can see in this plot, the light curve, in many days, you have daily variability, very strong. But it was really extremely powerful, this single point on the 12th of November 2012, where we had a very strong and high level variable emission flare. And it was so strong that we could divide the light curve, what you see here on the left, in a minute light binning. And you can clearly see that there are many sub-flares of the order of time of minutes, or even less than 1 minute. So what is the conclusion? The conclusion is that, yes, the emission region must be of the order of the same light horizon, light size of the black hole. And again, we have different possible scenarios, but in this work, we found that the magnetospheric model, so the emission really near on top of the black hole could be favored in this what we saw with gamma rays. So again, what we are looking here probably is the emission really near the on top of the black hole at the base of the jets. This was not the only one clue on this. There is another one on M87 again. This was an observation that was done on 2008. And you see on the right different light curves and different months period. And you see in this gray curve a clear gamma ray flare observed by all the present operational Cherenkov telescopes. And you see that this flare does correspond in X-ray to the emission in the nuclear region, not just, for example, in the HST knots along the jet. And also in the radio, you see that there is the emission rising in that period, respect to what you see, for example, in the jet. And this is also clearly seen in looking at the VLBA images before and after the flare with different epochs, where you clearly see I assume you can see it, let's say, hotspots going out of the main core of the radio core. And so the conclusion we had is that the gamma ray emission occurred really near at the base of the jet, because the core in this case includes also the black hole and the base of the jet. So this is again an indication that gamma ray emission may trace what happens on the base of the jet and near the black hole. And I think, I'm pretty sure it would be extremely interesting to observe such flares with the next generation ngEHT. And but unfortunately or fortunately, I don't know, the ngEHT first image was done during an epoch where the source M87 was stable and not really flaring, and this was also discussed yesterday by Christian Fromm and Svetlana in their talks. And so this is just to give you an idea of what we can do with gamma rays. But it's clear that gamma rays alone can tell part of the story. I also didn't mention other stories where, for example, it's clear that the emission comes out of the black hole very far. But just for a question of time, I refrain to do that. But it's clear that when we take gamma rays along with or together with multi-wavelength observations, really we can extract the full information on our source, and we can derive the properties which are related to the accretion, to the jet emission, to the jet formation, and so we can relate the connection between jet and the supermassive black hole. And it is clear that it was something that was done already with the ngEHT in the multi-wavelength paper that we published together. And it's clear also that for the magnetohydrodynamic modeling, these informations are crucial, not just to remove part of this phase space that could be simulated, and also to reduce the uncertainties in the models. And just to give you something that you know very well, I'm pretty sure, I mean, it's when you have an AGN or a blazer, and you look at the emission from the jet, you are dominated by two main non-thermal emission components, usually ascribed to synchrotron and then to inverse Compton. And these two emission components can be used to derive the physical parameters. For example, the self-absorption is used to have an idea of the compactness magnetic field, but also the emission power in the synchrotron is related to the magnetic field, and so on and so forth. Also, the main distribution that you see in the gamma rays is related to the distribution of the electrons generating synchrotron emission. All of them boosted by the beaming effects that you know are related to the jet relativistic movement. And then you have also other variability time to the variability time. But what I'm telling you is something that you know very well. I do not need to really go deep, because you also published, actually we also published together this paper with the multi-wavelength observation on M87, where we built the spectral energy distribution from radio up to gamma rays. And in that case, it was clear that we could not model the full picture. We cannot model the full set with a single modeling, with a single process, but there was a so-called heuristic process, and trying to describe this emission with two different components. One is a jet, probably at the base of the jet, which is more light, magnetic dominated, the Poynting flux dominated, and which describes the radio emission. And then we have an heavy, more particle dominated emission that maybe drives the high energy emission. But this is just something, it's just a starting point, because it's clear that in the future this should be done. I mean, the lesson we learned is that we need a detailed description of this spectral energy distribution to elaborate properly the gravitational relative, the magneto-hydrodynamic simulations, and to derive the variability studies on the sources, which are needed to understand the emission that ngEHT observes. And I would like to point out the importance of multi-wavelength observations. And so what does it mean? It means that we need a regular sampling that will allow us to understand which is the status of the source when we observe, or where ngEHT will observe, to also have an idea, for example, of quasi-periodic variability. And in the M87, there was a clear fluctuations or variation, which may be periodic in the image. And also, what is important in case of flares that, as you can see, can last days but also minutes, we need a real dynamic schedule. So we need to repoint our instruments as fast as possible. And with gamma rays, we demonstrated, I will not mention, but we demonstrated with gamma ray burst observation detection that we can really repoint our instrument within seconds. Okay, in this image, there is a sort of summary of what the technique is about. And the technique is about, I don't know if you can see my video, please tell me if you can see it. There is here the representation of the shower, particle shower developing into the atmosphere, producing the Cherenkov light, okay? And the reason why I'm showing you this video is that the main message here is that our instrument is the atmosphere. This is not a nuisance, this is not noise, it's what we use to detect Cherenkov light, and the telescope is just the final part. What we do with the telescope is just to determine the image of the Cherenkov light that is used to reconstruct the main parameters of the gamma rays that impact the atmosphere. Of course, there are other instruments like the Fermi LUTs that you can also see here in space, and that can reveal and detect the gamma rays direct. Okay, are you still there? Well, if I hope so. No, apparently
we are still here.
We hear you.
Okay, then this is, let's say, a description of the gamma ray sky, just to give you an idea of what we see at energies above 100 GeV. And here is the sky is formed now something like 200 or more than 200 sources. And in the extragalactic sky is dominated by blazars, AGN, and very few, a couple of FR1s or radio galaxies. So I will now go to the final part of the talk, which is the description of the Cherenkov telescope array, which means how what I have shown you can be improved in the next future. So the Cherenkov telescope array is, here you can see some figures, but I will go in some details of them immediately after. What you have to know is formed by different sizes of telescopes, large, as you can see in the image, medium and small. This is to cover the widest energy range, and it is shared in two sides, northern and southern. Another point that I think is useful to know that we have two different configuration, the so-called alpha configuration, omega configuration. Alpha configuration is the one that is already funded and that will start to take science in a few years from now. And the omega one is the one that we think will go at the end or will be built. And here you see the performances of CTA from the point of view of sensitivity. So on the y-axis, you have the sensitivity that can be detected with the observation of 50 hours. And on the x-axis, you have the energy. Now, this plot is a bit crowded, but just to make it more clear, this is the sensitivity curve of the present generation of the SCT, so MAGIC, HES, Veritas. And on the bottom, you have the sensitivity of the two sides, northern and southern side. The northern side is dominated in the low energy part, and the southern side dominates the high energy part. So I don't know if you can still hear me, yeah, because I see someone frozen. Yeah, okay. So, and what the important message here is that the sensitivity will improve 10 times more with respect to the present generation, which means the same source can be detected at the same sensitivity sensitivity level with 100 time integration time less. And this is clear, for example, also it's important for transient sources and flaring sources. So what does it mean? It means that with such a wide effective area, which is due to the fact that the telescopes use the atmosphere as a detector, and they are the final part of a broad Cherenkov emission. Thanks to this, the CTA can really have a boost in transient detection of transient of fast flares with respect to space observatory because of this effective area, which is of the order 10 to the 4 respect to Fermi lights, for example, at the same energies. And also from the angular point of view, the Cherenkov telescope array telescopes are characterized by a wide field of view, 8 degrees or something similar, and with the angular resolution that you see on the top right as a function of the energy, which is below, it's 6 primes, or let's say below 1/10 of degrees. And so you can see in these images compare, for example, to HES. And this is a big step forward in the morphological studies, for example. And now here, the main teams, scientific science team that will drive CTA observation. The first one is more something astroparticle related to astroparticle physics or cosmic ray. The second one is more astrophysical, so something which we are interested in with ngEHT, and the final one on fundamental physics. Now, what we did in the last few years was to build the so-called white book. So what you are doing also now with the next generation ngEHT, building a science working group and producing your goals for the next instrument. We did in this science with the Cherenkov telescope array book that you can find, and where we provided the overview and what we can get on different themes and different topics, and that you can divide it in surveys from on one side and some key objects on the other side. And of course, for ngEHT, I think the most interesting one are extragalactic topics. So, for example, the extragalactic survey and the active galactic nuclei that I will show in the 2 next slides. The first one is the extragalactic survey. It is an unbiased survey of 1/4 of the sky with a mild sensitivity, and we do expect to detect something like 100, 200 more sources. there. Also to build an unbiased luminosity function. Here in this plot, for example, you see as a function of the flux, the log n log s distribution simulated, and where you can see the improvement of the number of sources with the extragalactic survey. But then that we have also in these key science projects, we plan also to monitor some tens of AGNs of interest to have a real long-term monitoring of these sources, and to also derive a high-quality spectrum measurement on some specific targets. And among them, we have two radio galaxies that you know very well. And for example, in here on the bottom, you see the light curve that we do expect. I have shown already this one, but this is simulated with the CTA, and you can see that we can really detect flares in less than 1 minute. But also on the right, you can appreciate the precision, let's say, the quantity of information you can have with our spectrum. These are key science project program, but also we have the guest observing program. And just I'm now going to the end of my talk, describing you very shortly how this will work. This can be of interest also for you in case you are interested in CTA observations. Of course, we have the CTA consortium, which is something very similar to the people now joining here this next generation EHT meeting. And we are the one that produces the key science projects, and that we will propose to the CTA observatory that will give us the data. But of course, we have also the other communities, so they're all community interested in CTA that will propose the proposal, the guest observer proposal. Now, I finish with just describing you the consortium. The consortium is built with more than 1,000 scientists all around the world, as you can see here. And this picture shows, this picture shows the, this picture shows the last meeting in presence we had in Bologna 3 years ago, actually, and now are all online. And the final slide, just to give you an idea of what is the status of the CTA project. So this is the timeline. We are now in the design phase. There was an ERIC, which is an European consortium recognized in Europe that is going to be formed. It was approved, and it will be formed in the next year, so that the construction phase can start. And together with the construction phase, we will start on the science verification phase. So first science also results will be produced. And as you can see, the timeline is very much in agreement with the development of the next generation EHT. This is not just designing, this is things that are done and are working right now. So we have few prototypes which are already in operation. Here on the right, on the left, you see the large size telescope, the first prototype of the large size telescope together with the MAGIC telescopes that already produced some emission from the crab. And on the right, you see the small size telescope, in the middle, the Schwarzschild medium size telescope. And so this is, let's say, my conclusion. What I have shown you is that gamma rays, I think, are important to understand properly what is happening near the black hole and the base of the jet. This is what EHT aims at. And the multi-wavelength spectral energy distribution is important. And this needs integration between different observatories. And finally, the CTA, the next generation of Cherenkov telescope, will provide a deeper view in the gamma ray astronomy, and also related to the targets that are observed by EHT and the next generation Einstein Horizon telescope. And thanks for listening to me, and that's it.
Okay. Thanks to Antonio.
But since we have run out of time, so I think we will skip the question session, and
yeah,
as I see on the Zoom chat already, also people can talk on the channel. So I think we will take 5 minutes for break. After.
Yeah, that's right. That's right. Reconvene at.
So we will see you all in 5 minutes. Thank you very much.